Right, exactly, right? Don't forget to like and subscribe. So, like if I'm doing linear regression, for example, if I have all these data points, and it could be nonlinear regression, whatever, but let's say I have some data points of like, these are just some data points, and like what should we put on the axes here? Pick anything, I don't really care. What do we want to put on the x-axis? Time, okay. And what are we going to put on the y-axis?
Kilometers.
No, that's too, come on, that's too easy. Let's have more fun.
Height.
Pardon?
Height.
Height? Number of jumps, perfect. I like that one better. Number jumps. So apparently, something we're observing, it appears as if like, well, you know, it looks like as more time goes on, more jumps happen, right? Based on this data, right? That looks like what's going on there. And someone might say, oh, I want to be able to like predict. If I know how long it's been, I want to be able to predict roughly how many jumps will I have observed over time. Okay? Simple problem. I don't know if is this even showing up on the, yeah, it is a little bit. So what I'll do is maybe I'll fit a line. I'll fit a line, I'm going to find the best line such that every point is minimally far away from that line. So there exists a line such that it is the least far away from every point on this plot. And pretend this is a straight line. It fortunately goes through the 0, okay? And let's pretend that's that line. It's not going to be quite that line, but let's pretend it is. So far, we kind of understand what's going on. And so if I say, okay, so let's pretend it's been x time points, or like x units of time have gone by, and I want to know, like, well, how many jumps should I expect? I go, well, that's easy, right? You just go like, let's pretend it's right there. I would expect that many jumps, right? Pretty straightforward, pretty easy to understand. Why did you predict that many jumps? Well, because, you know, if we look at all the data, we can see that there's this trend. And if we've, like, you know, the line that we have that best fits the data we observed lets us know that we should expect around that many jumps. Cool? That's the idea. This is a very simple form of machine learning. So simple that a lot of people would say this isn't even machine learning, but it totally is. So there we go. That is a very simple form. There are other very simple forms of machine learning. Who here knows what like k-nearest neighbors is? Okay, so for those of you that don't know, now let's go over here and I'm going to draw a plot. Give me two quantifiable things for the axes. Anything. Number of keys lost. Ha 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 ha. Keys lost.
Delay, time delay.
And time delay. Usually time would be on that axis, but well, whatever. Let's do time.
Time could be on any axis, really.
Delay.
Yeah. Getting to class.
Right? And then let's say we have students and professors, okay? We have all these observed data points. There we go, right? And then I come across, somebody comes running in the room, we've never seen them before, okay? And they say, I've lost this many keys, and I was this late, right? So we're looking right here. Based on what you see, what would you say, are they an X or are they an O?
Most likely an X, could be an O, not unreasonable.
It wouldn't be crazy to think it's an O, but you know, it looks a lot more like the X's, right? It's closer to the X's. Looks like a duck, it quacks like a duck, it's probably a duck. That's K nearest neighbors, right? K as in, well, how many neighbors do you want to look at and how many are the closest? Well, based on what I've seen, it looks like it's pretty damn likely that it's going to be an X. That's another form of very simple machine learning. And when I say simple, I don't mean useless. This is the type of machine learning, this is the type of optimization that if you have a problem and you want to solve it, that's what you want to use. You don't want to use evolutionary computation. You do not want to have to use neural networks. You want to use the simplest stuff possible because it's well understood, it's easy to explain, it takes no time to implement, and it takes no time to train. It's easy to test. There's so many reasons we prefer this. So this is another form of simple machine learning, right? So if the physician comes in and says, why do they need neurosurgery? I could be like, well, okay, based on all this data, we can see that almost always, based on the data, that they need neurosurgery because everyone else in that area, you know, I can at least explain. Doesn't mean they're going to listen to me, but I could at least explain. Where a neural network is more like this. Input, output. Data patient information, give them neurosurgery. Why? I don't know. This is supposed to be a black box. Why? Because my magic black box told me so, and it's right almost always. Yeah, it's not really going to work. Now, I should be nice to evolutionary computation, on the other hand, because sometimes evolutionary computation in terms of like how you're using it, what you're doing with it, sometimes it's black boxy, but sometimes it's actually very describable, very explainable, which is a good thing. You may have heard like the buzzword, it's been popular for a bit, explainable AI. That would be like, we want more explainable AI. Anyways, where was I going with this? I was talking about neural networks, talking about how they're black box, hard to understand. Where was I going with this?
You want to solve a problem, don't toss a dart to the dartboard?
Yeah, that's right, but there was something I was getting at before I got to that part. Why did I start talking about neural networks? Yeah, that machine learning video. It started from, I'm trying to retrace the thoughts, but you're right, that's a good, okay. Okay, well anyways, the history. You go back to like, let's say the 80s, 90s, the neural networks, they kind of worked, but the other simpler forms of machine learning worked better. So they were easier to understand, both in terms of like training and results. They were easier to train, easier to test. They gave good results. Like, obviously, why would you go out of your way to use like a shittier technology that's way harder to use when you could use an easier, simpler technology that's better, right? It was great. But then as time went on, and like people who really liked neural networks were like the kooks. They were the weirdos. Like, what are you doing? You're wasting your time. Now, in the realm of like basic science and like understanding things for the sake of understanding things, that's fine. But when it comes to like the utility, people were like questioning, why are we doing this? But as time went on, turns out neural networks are a great idea. With neural networks, they take a lot of computation to train. They're hard to understand. There's a lot of reasons why we don't like them, but they work really good in practice. Unfortunately, like evolutionary computation, to get the best results that we can get out of these things, you need crazy amounts of computation. Like you need billions of dollars of infrastructure to train, and then you get good results. But neural networks tend to scale a lot better than evolutionary computation. You can go download a neural network framework on your computer, build and train a neural network, and get really good results. You can with evolutionary computation too, don't get me wrong, but neural networks are pretty damn good at that level of like what you have resources. Another thing with neural networks that you don't really get with evolutionary computation is with neural networks, you can download pre-trained models. Basically, some people have spent a lot of money to train these networks on like general problems that you can take and fine-tune for your specific problem really well. So they've kind of like done a lot of that training for you such that you only need to do a little bit more to get really good results. So anyone can use it really easily, where you can't really do that with evolutionary computation. At least no one's figured out a good idea for that yet. So a lot of these like things in the computational intelligence world, we are really limited by our computing power, for better or worse. Some people like to say like, oh, my algorithm's so good that our computers can't keep up with it. Okay, that's kind of a weird attitude, because like the way we make advances in this technology is how you make these algorithms work better with less resources, right? You don't want to use all that resources if you don't need to. And evolutionary computation is pretty wasteful in terms of computation power. Like how many times are you evaluating the fitness of stuff that's ultimately useless, right? I mean, you could argue how useless is it, because you need to know how good everything is to know which ones are the relatively good ones. So you need that information. But at the end of the day, we're throwing away a lot of that work. So, and you know, over the last few years, people have become very like aware of the literal like power energy cost of running these algorithms, and like people will literally start like calculating like greenhouse gas emissions that are associated with training these algorithms. It's not like it's a crazy amount that you're going to be doing when training this. It's not like you're killing the planet or anything, but you know, you put it into that perspective, it kind of changes how you think about these things. Anyways, so when that video, like what's the channel guy's name? Like CGP Grey or something?
CGP Grey.
Yeah, most of you probably know who that is. He's a YouTuber, right?
It's mostly a history
YouTuber. I
YouTuber.
mean, he was popular, like, he was more popular, I'd say, years ago, but then like a lot of other more popular people came, whatever. Anyways, it doesn't matter. He had this video that came out a few years ago, and he was talking about like, he was really talking about like how these like algorithms learn, but the way he was describing it was more like neural network, or it was more like evolutionary computation, which I was like, oh, that's pretty exciting, because you don't really see that very often today, because everyone's talking about neural networks.
I feel like Code Bullet would be a better example.
What's Code Bullet?
Is the best example, because even right now he's doing evolutionary.
Who's Code Bullet?
YouTuber.
Oh.
Code Bullet YouTuber, kind of similar to CG.
I'll have to check it out. I'm surprised I've never heard of this person before.
He mainly does like, let's recreate a game and then use evolutionary computation to have fun with it. That's it.
I'll have to check him out later. Neat. Literally never knew of this person. It's weird that I haven't. Anyways, where we were last time was here. We were finishing off the non-numerical hyperparameters. Raise your hand if you're like, yeah, I finished what I wanted to do and I tested it. Okay, 2 people. Raise your hand if you're like, well, if you give me 5 minutes, I will. Yeah, okay. So take 5 minutes, keep hacking around, play around, make sure you run it a couple of times to get a sense of where it is. And then we'll come back and we'll talk from here. I'll pause the recording. I'll assume you've had a chance to go over what you've done. So based on this, who here created their own crossover function? What was it? What did you do?
Basically.
They had 2 chromosomes.
Yeah, we basically kind of did a card shuffle kind of thing. So
You
know
like-
how Pharaoh card shuffling works, where it goes from one then the other. We made one large set, and we took from the 2, one from pair 1, one from pair 2, and we kept doing that. And
Like randomly one from each.
We didn't do it randomly, we just did, because it was in order. We could have done it randomly, but we just did
that was our
1, 2,
next
1, 2, 1,
plan. Was to
So you kind of like zipped them together
Yeah,
Yeah.
we did this, and then cut it in half.
and then cut it in half.
yeah.
Okay, how'd it work?
Surprisingly well. I think it
Yeah.
worked better.
I would say it was about the same.
Yeah.
Based on randomly.
For a problem like this, I would...
It's faster.
Interesting. For a problem like this, I would assume something like that would be kind of... The problem's... I don't want to say it's uninteresting, but the problem is simple enough, and there's not a lot of things to exploit in it, where like an interesting crossover will have a huge impact, but interesting idea. It didn't not work. Hey!
It seems to peak faster.
Yeah. Well, there you go. Well, that's good. That's good. Anybody else? What did somebody else try?
I tried a crossover function where it went through one of the lists, like the first list, and randomly switched the bits in between both lists, just like completely at random.
Okay, so like, would they be in order though? Like if I, like, would it be like, okay, do I switch them? Do I switch them? Do I switch them? Like that type of thing? That's actually called like, I believe that one's called like order crossover. So that's actually like
Oh, okay.
a maybe common isn't the right word, but like a well-defined one. So there you go. Your head's in the right spot. Well done. What else did somebody try? Anything else? What did you try?
So I took the two separate lists and then I randomly flipped a coin, so 50-50, and then if it was like above 50%, then I take that index of one, and then if it was below.
So like kind of like what he did. Yeah, that's like order cross. I believe it's order cross. Maybe it's uniform. Maybe that's uniform crossover. Maybe it's called uniform crossover. I could be wrong. Whatever. Either way, that is a one people would do. Well done. Well done. What did you do?
I just literally just like randomly pick like a bit. It's just like to pick like 1 or 0, and then like where I get, I then find a 1 or 0, and then like switch that.
Okay. Interesting. Now, how about mutations? What did people do for a new mutation idea?
We didn't get to it.
You didn't get to it? You were having too much fun with crossover. Okay. Anyone do a new mutation?
I had an idea for a mutation. I didn't get to it, but I had an idea for a mutation where I would basically have a random chance to completely generate a new string.
Okay. There you go. Okay. Interesting. Interesting idea. I'd like to see how that would work. Probably would work just fine. Neat. What about you?
I did not get to mutation.
Everyone was just having too much fun with crossover. Yeah. I should put crossover later because I think it's harder to do something than like mutation. But how about select? Did anyone implement a new selection? I mean, if you didn't do the mutation, you probably did the selection.
We literally went through crossover. First, we were trying to figure out what the first crossover, because we looked at your crossover things. One was one's crossover, and then the other one.
Oh yeah, I had implemented
Yeah.
some crossover.
We
No,
also
that was
did-
with one's fitness. It was one's fitness.
Oh, it was 1 point crossover.
1 point crossover.
And then
Okay.
whatever the other crossover was, we were trying to read through that and understand it, and we were so confused.
You were cheating. You were supposed to invent your own.
That spent most of our time.
Okay. All right. Maybe I should have given you more time.
The two that were made before we created one.
Did anyone else like hack anything into their GA to see if it did anything different, if it improved anything? I guess maybe I should have given you a little bit more time, but whatever. At least the point here is I guess we could make these questions more rhetorical. Like, you could invent your own mutation, and maybe you should. See what happens. Your own selection, maybe you should. See what happens. Did it work? Did it not work? Just because it didn't work here doesn't mean it wouldn't work somewhere else. And just because it did work here doesn't mean it would work somewhere else. All of this stuff is it's a complex system. Any change you make, you don't know what the hell it's going to do. The new selection you invent might only work really well if you also have 1 point crossover. If you change it out to 2 point crossover, your selection might go to shit. Who knows? Like all that stuff's all over the place. Yeah.
Is it a valid crossover if you just switch from one bit?
Yep. All that matters is that you exchange information from one to the other. That's it. Information is exchanged between two candidate solutions. If your function does that, it's a crossover. Doesn't mean it's good, but it's a crossover. Yeah?
I had an idea for kind of like a hybrid mutation crossover thing where it would if it was chosen to crossover, it would randomly generate a new string and then make the second list like the mirror of the other one.
Interesting. Okay, so you would that's an interesting one. That's not really it's not really crossover, but it definitely falls into like the realm of, it's definitely a variation operator, with like a genetic operator. It's like a crossover or a mutation. But I don't know if I'd classify that as a crossover. People could probably get lost in the sticks of like a semantics discussion there, but it's an interesting idea nonetheless. People will ask, can I do crossover between, why stop at exchanging information between two candidates? Why not do like a 3-way crossover? Sure, go for it. You could do whatever the hell you want. Any other questions before we move on? All right. So what we've done so far is, you know, I gave you a high-level view of what what evolutionary computation is. That simple picture, right? Start, evaluate, select, variation. Evaluate, select, variation. Evaluate, select, repeat, 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 and then end eventually. That's really evolutionary computation right there. Then I went on to explain, okay, well, here's a GA. A GA is a very common, it's probably the most common form of evolutionary computation. It's relatively simple. It works reasonably well. It's good at what it's good at. But it's by no means what you should use in all situations. It's very common. It's easy to understand. People like it. And then we implemented it. So now you know like how these things work, but we really haven't taken a moment to talk about the problems that we could really realistically want to use the stuff on. So we kind of like jumped into the deep end so you knew what was going on. And now we're going to kind of take a couple steps back and like start back near the beginning along a different route. And I think things are going to fit together really nicely. By the way, the first assignment does have a due date now. I said it. It's like October 7th or something. It's like the first Monday in October. So is it not there? Hit refresh, hit refresh. Oh, maybe I didn't merge the PR yet. Did you hit F5? Oh, okay, maybe that doesn't work on Mac.
I see it here.
Hit it again. Still not there? You saw it?
It's on GitHub. You
Is it on the Moodle?
If you go to GitHub, maybe I haven't merged the PR yet.
I have it set on the Moodle page, but I didn't see it on the website.
It's set on the Moodle page. Okay, it's set on the Moodle page. I must not have merged the PR to the website. Whatever, it's going to be there. If you go to GitHub, you'll probably find the pull request that says, make the due date. Here, let's make sure I'm not crazy.
Yeah, I see it.
You do? Yeah? My apologies, I jumped the gun. It's almost. Add due date for assignment 1. No, I didn't test it. See, it's there, I swear, October 7th. Yeah, all right. That will be reflected shortly. But you now know what I have in mind. Anyways. All right, back to this. So the problems. Okay, we've got genetic algorithms. I talked about computational intelligence. We're in the realm of AI, machine learning, optimization, whatever. What are we using these for? Well, the maximization of a decimal integer of any unsigned binary number was a toy problem. Toy problems, even being generous, it's a contrived, silly little problem for demonstration purposes of, okay, what the hell's a GA? It's trivial, but it's easy to understand. And it gave us a chance, like think about, like with crossover, right? Remember how I feel as if it was a good problem to show you how crossover alone is problematic because like, well, what happened? Crossover is great for exchanging information that exists in the population, but it can't add new information to the population. If we had a population full of candidate solutions where none of those candidate solutions had a 1 in index 7, there's no way to add a 1 to index 7 to any of those candidate solutions with crossover alone. It ain't going to work. Yeah.
Technically, ours could do it because
Yeah.
of the way it
Yep.
shares them around.
So, but with this one, we're limited. It didn't really add that new information. And then once we get to that, we start to get to situations where we start to talk about like order. And that's when we start talking about representations in a little bit more detail, which is a soonish topic. We'll learn a little bit more about that type of stuff. Usually, like I've been saying, we're not using evolutionary computation unless we've got a hell of a hard problem, where no other good strategy for solving the problem would be used. We use it as like a last resort. It's very computationally expensive. It's hard to understand compared to algorithms. And it's notorious for overfitting as well. Like a lot of these like heavy-duty algorithms, they overfit. Anyone know what overfit means? Let me show you.
It becomes way too specific to the task at hand.
Yeah, and it ends up sucking. So let's go back to like the problem of X's and O's, right? Let's say we're not doing k-nearest neighbors. Let's say we're doing like some sort of nonlinear regression for classification. Trying to think. In any system that you're observing, there's going to be some noise. Okay? Meaning, there's always like outliers for anything you observe. So if I'm doing some sort of classification algorithm here and I want to classify X's and O's, I might be able to get away with drawing a boundary. And my boundary might look something like this. Okay? Anything down here is likely to be an O. Anything up here is likely to be an X. But you can see it's not perfect. And that's because, I mean, based on the data I have, if I make another observation that's not in this data, if I make another observation and it goes here, let's say, what should it be? Is it an X or an O? Well, I mean, it's kind of on that boundary line where things are fuzzy. We don't really know. So we got to be very careful in situations like this to not overfit. So any classification with real noisy data, it's not going to be perfect. There's always outliers that mess things up. There's noise in the data. Who knows what happened? Maybe that plant had a mutation where it grew a bigger leaf, which made it get misclassified. Stuff like that's going to happen, right? So this is a boundary. We like boundaries like this. Overfitting is if you have an algorithm that's just trying way too hard to fit the data, where you end up with something like this, where the boundary looks like this. All right? And then, you know, I might put something like, well, okay, if there's an O here, it was probably going to be on this side of the line if it wasn't overfit, but because we overfit, now it's like, whoa, no, it's totally an X. But you know, this one kind of messed it up. This was the outlier, not this one. So overfitting is it's trying too hard to the point where it fits the training data too well, and then any new data, it sucks at classifying. Stuff like that will happen. All right? So overfitting is when it's just trying too hard. And these heavy-duty algorithms are notorious for overfitting. You have to be very careful with this type of stuff. So yeah, so for learning purposes, classic toy problems are used in this course. And when I say toy problem, some people are really obnoxious. When I say toy problem, I don't mean it's a useless problem. Some toy problems are actually very important problems, like traveling salesperson problem, for example. But some people get pissy about the word toy problem, but toy problem, I'm using that as like it's a model problem, something that we can understand well and talk about in terms of what we get. It's important to know, though, at the end of the day, even though I'm talking about like toy problems, it's important to know what types of problems evolutionary computation is realistically appropriate for. It's a bit of a joke in the world of like machine learning, AI optimization, where, does anyone know, raise your hand if you know what FizzBuzz is. If you've taken 161, you know what FizzBuzz is. It's that problem, you know what it is. It's that problem where, okay, and it used to be like a classic interview question. It's a simple problem, but it's a good problem. It's, okay, by the way, y'all are screwed for finding jobs. You want to know why? Because you go back in time, those interview programming questions were a little, maybe simpler isn't the right word, but more straightforward. But over time, websites like LeetCode and whatnot popped up, and then everyone became expert on these like little like interview style questions. And so those questions started getting more and more and more crazy complex for the sake of like weeding out candidates. But you go back in time, the questions people would ask for like junior programmers would be questions that are like, they're simple questions, but they're good at like distinguishing what you do and you don't know. And one of the common, very simple problems, now this wouldn't indicate whether or not someone should or should not be hired. It's just, it's a problem to know, does this person know the basics of programming? And the question was FizzBuzz. FizzBuzz is Okay, you're going to start at 0, or let's say 1, and work your way up to 100. And you're going to say, whenever you look at a number, if you see a number, you print it out. So you look at 1, you print out 1. However, if you see a number that is divisible by 3, instead of printing out the number, you say fizz. And if you see a number that's actually divisible by 5, you say buzz. And in the situation where you see a number that is divisible by both 3 and 5, you say fizzbuzz instead. So you look at 1, you say 1. You look at 2, you say 2. You look at 3, you say fizz. 4, 4, 5, buzz. 6, fizz. 7, 7, 8, 8, 9, fizz. 10, buzz. 11, blah, blah, blah. 15 would be fizz buzz. It's divisible by both 3 and 5. That's fizz buzz. And there was this joke that came up a couple years ago. I could find it. Oh, come on. I think this is it. Maybe this is it. No. Why can't it? Yeah, here we go. And this is like a joke, like blog post from a programmer about like, okay, it's the situation where they are this hypothetical interviewee for a job and they're given the problem fizzbuzz, and they're like, all right, well, let's load up TensorFlow to do this, right? Like a TensorFlow for making neural networks. They were using heavy-duty machine learning AI to solve the problem of fizzbuzz. You don't need the neural network to solve fizzbuzz. That's a stupid idea. But it became a joke at the time, and it had been a joke before this. This was written like 2016. And before this, people were making fun of this stuff, where people would be given a problem, and then they'd throw a neural network at it. And people would be like, no, do linear regression. It'll work just fine. And then this person took it to the stream with fizzbuzz. It's just 3 if statements, right? Like that's all fizzbuzz is. And it goes through this hypothetical situation of them loading up TensorFlow, and the interviewer is like, let me make sure you understand the question. Like, oh yeah, for sure, here we go. What we're going to do is we're going to create the neural network. Anyways, and then they show their output. And funnily enough, it's not right all the time. Fizz, buzz, fizz. Fizz, buzz, yeah. Fizz, buzz, 17, 19. There are mistakes in here somewhere. Anyways.
21.
21, yeah. So it's like a meme in the AI machine learning optimization world of like people getting a little crazy about using machine learning when they shouldn't, or hell, using the big guns when they really shouldn't. Anyways, we'll pick up here on Friday.
Actually, it has 2 fizzes, one right after the other.
Fizz, fizz.
At the very end.
Makes perfect sense. Point being, like,
100 is divisible by 3.
yep, makes sense.
I'm actually surprised.
Yeah.
I would not expect it to get something like that wrong, but you know what?
Maybe if you let it run a little longer, it would have been fine. Or maybe if you wrote the 3 if statements, you know. Anyways, that's where we'll stop for now. And wish me luck in finding my keys.